Humanity has always looked up at the night sky with curiosity, fear, and wonder. For thousands of years, the stars were distant lights, unreachable and mysterious. Today, we are living in a historic era where space is no longer just something we observe. It is something we actively explore, study, and prepare to inhabit. Recent breakthroughs in space technology are transforming our understanding of the universe and reshaping humanity's future beyond Earth. From the James Webb Space Telescope revealing alien atmospheres and ancient supernovae, to revolutionary propulsion concepts that could one day take us to the stars, to artificial intelligence mapping entire galaxies, space science is entering a golden age. This video explores the most important recent space technology breakthroughs, the key trends shaping the future, and how these developments could redefine life on Earth and beyond. We begin with one of the most powerful scientific instruments ever built by humans, the James Webb Space Telescope. The James Webb Space Telescope, often called JWST, is not just another space telescope. It represents a complete leap forward in how we observe the universe. Unlike the Hubble Space Telescope, which primarily observes visible and ultraviolet light, Webb is designed to observe the universe in infrared wavelengths. This allows it to see through cosmic dust, peer into stellar nurseries, study distant galaxies, and analyze the atmospheres of exoplanets in extraordinary detail. One of the most revolutionary achievements of the James Webb Telescope has been the detection and analysis of atmospheres on rocky exoplanets. For decades, scientists have dreamed of studying Earth-like planets orbiting other stars. While we have discovered thousands of exoplanets, understanding what they are actually like, whether they have atmospheres, clouds, or even conditions suitable for life, remained extremely difficult. Webb has changed that. Using a technique called transmission spectroscopy, the telescope observes light from a star as it passes through a planet's atmosphere during a transit. Different molecules absorb specific wavelengths of light, leaving behind chemical fingerprints. With this method, Webb has detected molecules such as carbon dioxide, water vapor, methane, and even hints of complex chemistry in the atmospheres of distant rocky worlds. This is a massive breakthrough because an atmosphere is a key requirement for life as we know it. An atmosphere regulates temperature, protects a planet from radiation, and allows liquid water to exist on the surface. By identifying atmospheric compositions, scientists can now classify exoplanets more accurately and prioritize which worlds are most promising for future study. Beyond exoplanets, the James Webb Telescope has also allowed astronomers to observe the earliest supernovae in the universe. Supernovae are the explosive deaths of massive stars, and they play a crucial role in cosmic evolution. These explosions create and distribute heavy elements like iron, oxygen, and carbon, the very elements that make planets and life possible. By observing supernovae that occurred shortly after the Big Bang, Webb is helping scientists understand how the first stars formed, how galaxies evolved, and how the universe became chemically enriched. These observations are pushing our cosmic timeline further back than ever before, offering a glimpse into the universe's infancy. While telescopes like Webb help us observe the universe, another major frontier lies in how we travel through space. Traditional rocket propulsion relies on chemical reactions, which are powerful but extremely inefficient for long-distance space travel. Even reaching Mars takes months, and interstellar travel using chemical rockets is practically impossible. To overcome this limitation, scientists are exploring entirely new propulsion concepts, one of the most promising being high-speed electron beam propulsion. Electron beam propulsion is based on advanced plasma and particle physics. Instead of expelling heavy propellant like chemical rockets, this concept uses streams of high-energy electrons, accelerated to near light speeds. These electrons interact with electromagnetic fields to generate thrust far more efficiently than conventional engines. The potential advantages of this technology are extraordinary. Electron beam propulsion could achieve much higher exhaust velocities, meaning spacecraft could travel faster while using less fuel. This opens the possibility of rapid missions to the outer planets, and, in the very long term, even interstellar probes capable of reaching nearby star systems within a human lifetime. Although this technology is still largely experimental, progress in particle accelerators, superconducting materials, and plasma control systems is bringing such ideas closer to reality. If successfully developed, advanced propulsion systems like this could mark the beginning of true, deep space exploration. Another transformative force reshaping space science is artificial intelligence. Modern astronomy generates enormous amounts of data. Telescopes like James Webb, ground-based observatories and space missions produce petabytes of information. Analyzing this data manually would take centuries. This is where AI and machine learning have become essential tools. AI algorithms are now being used to model galaxy formation, classify stars, detect exoplanets, and identify rare cosmic events. Machine learning systems can recognize patterns in astronomical data that humans might miss, allowing faster and more accurate discoveries. For example, AI models can simulate the evolution of galaxies over billions of years by analyzing gravitational interactions, dark matter distribution, and star formation rates. These simulations help scientists test theories about how galaxies like our Milky Way formed and evolved. AI is also revolutionizing how we search for exoplanets. Automated systems analyze subtle dips in starlight caused by transiting planets, distinguishing real signals from noise. This has dramatically increased the rate of exoplanet discovery. Beyond pure science, AI plays a crucial role in spacecraft operations. Autonomous navigation systems allow probes and rovers to make real-time decisions without waiting for commands from Earth. This is especially important for missions to Mars and beyond, where communication delays can last minutes or even hours. As AI systems become more advanced, future space missions may rely heavily on fully autonomous spacecraft, capable of exploring distant worlds with minimal human intervention. Another exciting area of development is space-based solar power. Earth receives an enormous amount of energy from the sun, but solar power on the ground is limited by weather, night cycles, and atmospheric absorption. Space-based solar power aims to overcome these limitations by placing massive solar arrays in orbit, where sunlight is constant and uninterrupted. These orbital solar power stations would collect energy and transmit it to Earth using microwave or laser beams. The energy could then be converted into electricity at ground-based receiving stations. The concept has existed for decades, but recent advances in lightweight materials, wireless power transmission, and robotics have revived serious interest. Space agencies and private companies are now conducting experiments to test key technologies required for space solar power. If successfully implemented, space-based solar power could provide clean, renewable energy on a global scale, helping to address climate change and reduce reliance on fossil fuels. Closely related to space-based infrastructure is the development of quantum communication technologies. Quantum communication uses the principles of quantum mechanics to transmit information securely. One of its most important features is quantum key distribution, which allows two parties to share encryption keys in a way that is theoretically impossible to intercept without detection. Space plays a crucial role in global quantum communication networks. Satellites can transmit quantum signals over long distances, bypassing the limitations of fiber optic cables on Earth. Several experimental satellites have already demonstrated space-based quantum communication, marking the beginning of a new era of ultra-secure global networks. In the future, quantum communication satellites could protect sensitive data, financial systems, and national security communications from hacking. While advanced technology expands our reach into space, robotic exploration remains the backbone of discovery. Robotic missions have explored every planet in our solar system, landing on Mars, orbiting Jupiter and Saturn, and even touching down on asteroids and comets. These missions pave the way for human exploration by gathering data, testing technologies, and reducing risks. One of the most ambitious ongoing efforts in human robotic cooperation is NASA's Artemis program. The Artemis program aims to return humans to the moon and establish a sustainable presence there. Unlike the Apollo missions, which focused on short visits, Artemis is designed for long-term exploration and infrastructure development. Central to Artemis is the construction of the Lunar Gateway, a space station that will orbit the moon and serve as a staging point for surface missions. Astronauts will use advanced landers to reach the lunar surface, conduct scientific research, and test technologies needed for future Mars missions. The moon is seen as a critical stepping stone for deep space exploration. It offers valuable resources such as water ice, which can be used to produce oxygen, drinking water, and rocket fuel. Establishing lunar infrastructure could significantly reduce the cost of missions beyond Earth. Robotic systems will play a major role in building and maintaining lunar bases. Autonomous rovers, construction robots, and 3D printing technologies may be used to create habitats using lunar soil. Beyond the moon, Mars remains the ultimate target for human exploration. Advances in life support systems, radiation shielding, and in situ resource utilization are bringing the dream of human missions to Mars closer to reality. Robotic missions are already testing technologies for producing oxygen from the Martian atmosphere and identifying potential landing sites. Private companies are also becoming major players in space exploration. Reusable rockets, commercial space stations, and private lunar landers are transforming the economics of spaceflight. Competition and innovation in the private sector are accelerating progress at an unprecedented pace. As we look to the future, several key trends stand out. First, artificial intelligence will continue to become more deeply integrated into every aspect of space exploration, from scientific discovery to mission operations. Second, advanced propulsion technologies will gradually reduce travel times and expand our reach deeper into the solar system. Third, space-based infrastructure, including solar power stations, communication networks, and lunar bases, will shift space from exploration to utilization. Fourth, international collaboration and commercial participation will shape a more connected and competitive space economy. These trends are not just about science and technology. They raise profound questions about humanity's place in the universe. Are we alone? Can life exist beyond Earth? Will humans become a multiplanetary species? The technologies being developed today are laying the foundation for answers to these questions. We are witnessing the early stages of a transformation that could define the next 1,000 years of human history. Space is no longer the distant frontier. It is becoming the next domain of civilization. As telescopes peer deeper into the cosmos, propulsion systems promise faster journeys, AI unlocks hidden patterns, and humans prepare to return to the moon. One thing is clear: the future of space exploration is not science fiction. It is happening right now. And this is only the beginning.